Welcome back to everyone. We are ready to restart with our session. The next speaker just a moment, searching for the agenda. The next speaker is Rosario De Rosa. Is there, Rosario, are you there?
Yes, can you hear me?
Yes, Rosario. You can try to share your screen. Rosario will give us a presentation about the environmental noise measurements at Sostenatos. We can see it, Rosario.
Okay.
You have 15 minutes from now.
Okay, thanks, Domenico. Good morning, everyone. We speak about the environmental noise measurement performed up to now at the Sostenatos site. And first of all, I want to thank all the people involved in this activity. I presented a short list, but for sure I forget someone. So let me apologize for this. This is a brief outline of my talk. I will give you the status of environmental monitoring in Sostenatos. Then I will focus mainly on the magnetic noise measurement, in particular for their motivation, comparison with Virgo. The only one comparison is available up to now. Then I will show you some comparison between surface and underground magnetic noise measurement and the in-time analysis. So I give you a brief focus on the next steps to conclude this activity. So the first probe in Sostenatos, apart from seismic probe that Luca and also Gilberto already talked about, were a magnetometer, the same kind we had in Virgo for for electromagnetic noise measurement, and a microphone, and they were installed in June 2019. Both of these probes were installed at level 2, that means about minus 100 meters underground. The magnetometer is still working, but the microphone just take data for 1 day. The very early results are shown in this slide. We had encouraging result from the initial measurement in terms of noise floor. In particular, the magnetic noise was a little factor 5 less factor 2, depending on the frequency band, less than what we measured in Virgo by using a magnetometer placed outside from the experimental hall, so well shielded against the noise produced by several devices we have inside the experimental halls. At the beginning, we had a lot of lines, but then after careful repositioning of the instruments and the data logger, we were able to cure all these lines observed in the blue spectrum. Instead of, the acoustic noise was very encouraging since the beginning, and the measurement spectrum that you will see in this slide was close enough to the instrumental noise. The current status is shown in this slide. We have a number of probes. I don't want to enter in the details, but we have 2 magnetometers working and a weather station. And while the microphones are on site, but they were not installed yet. You already see this photo. We have the magnetometer at level -2 and the surface working. And the other probes, I mean, the microphone will be installed the next year. You can see in this slide some photo of the installation and the positioning of the 2 magnetometers, underground and surface. The weather station is collecting data since last June, and the data summary are available on web. And I will show you now just the monthly report updated to the last Sunday, so a few days ago. What is the main motivation for magnetic noise measurement? So the noise can be produced by anthropogenic electromagnetic field or even from natural sources. And this kind of noise can affect the sensitivity of the interferometer in several ways. So by direct coupling with actuators, magnets, or other of the mirror and suspension system, or coupling with electronic devices managing the interferometer. This is a very general rule. And a special role about among the possible noise of magnetic origin are played by the Schumann resonance, that are worldwide electromagnetic field that are continuously sustained by discharge due to lightning between the Earth's surface and the ionosphere. These are very... Sorry?
Cioè, se io ho il valore nominale, posso...
Okay, there was some noise, acoustic in this case. So since these kind of disturbances are global, they can set a strong limit in the detection capability of, for example, for stochastic background, even if we assume a non-correlated noise between far detector. In particular, there are studies about this, and by assuming some particular power law in the behavior of the parameter omega, GW, we can see that in this figure that in some band the Schumann resonances can already limit the sensitivity of an interferometer. So it is very important to take this kind of disturbances well monitored and to take into account their effect on the machine. If we compare the magnetic noise in Sossenato, we will see, as I already showed in the previous slide, but after the cure that removes the lines, you can see in this slide two comparison between the magnetic noise measured in Virgo with the two magnetometers oriented towards north and west direction, the red and the orange lines, compared with the Sossenato underground magnetometers. And you can see clearly that the noise is lower. You can clearly see the Schumann resonance structures along this curve. And you can see that, as expected, you will measure a different noise level between the night, the first plot, and the day, the second plot. This is a spectrogram in the period from 6 August to 9 November, so the last 3 months, more or less, and are compared the response of the instrument in surface, the first plot, the upper plot, and the one in underground, the lower plot. You can see that the main value are very similar, but there are a lot of disturbance, especially in the surface instrument, while in the underground instrument you can clearly see always once more the Schumann resonance. Only a few of them are shown in this plot, and so this confirms that the underground location is very quiet, apart from disturbances that you can see time to time that are essentially due to disturbance on the mains. If you perform a statistics of the spectra collected during this period, almost 97 days, you can see that the lower limit, the 10th percentile of the underground instrument, is very close in low frequency to the sensor noise, and that also the median of the underground instruments is close to the 10th percentile of the surface instruments. This is natural, and this is expected, since the surface instruments is often disturbed by human activity that happen in the control room of the Sargrave laboratory. Data are collected in Sossenatons, and they are, in particular, only the data coming from the underground instrument are sent together with the seismic data to the INGV collecting system, and then are transmitted to the EGO computing center, and magnetic data are stored in a computing center at EGO, and then they are converted in another format and are sent periodically, 4 minutes if I remember well, to the Open Lab, sorry, to the VLF Open Lab for the Intime analysis that is managed by Renato, and that provide us very beautiful analysis like this one that already Luca has shown. And this is, for example, a spectrogram with 5 days of data in which you can recognize several features, in particular disturbance on the mains and Schumann resonance, and time to time some large glitch affecting all the spectra. If you look at some detail of this kind of spectra, you can better recognize some structures. In particular, of course, we see very very well the 50 Hertz mains, but we can also distinguish the 60 Hertz mains due to the mains distribution used in US. The Schumann resonance, as I already saw, and this is very particular spectrogram, since you can recognize here a pulsation, a magnetic pulsation type 1, and some spectral resonance structure. These phenomena are all typical of magnetic wave that stands in the magnetosphere of the Earth and are driven by solar wind or other phenomena.
5 minutes.
In particular, thanks. In particular, the same kind of pulsation was detected in another observatory. You can see the shape is very similar. That is located very close to Arctic Cycle in Finland. The name is Sodankila Geophysical Observatory. That is a geophysical observatory that monitors several features of the electromagnetic waves standing in the atmosphere. And this is a very good result, since this confirms that the sites, in particular the underground sites, is enough quiet from the point of view of magnetic noise disturbances. The next step for this activity, that as I already said, there are several parts missing from the environmental monitoring system for the site. In particular, at the beginning of next year, we will restart the collection from surface magnetometer that was temporarily stopped during since 2 weeks ago. And we will install also a microphone initially in surface for testing purposes, and then at level -2 for correlation with the seismometer. We do not expect to observe large acoustical noise, but we will use such probes just to perform correlation with other disturbances like seismic and magnetic also. And then we will install also the third magnetometer underground in SO3, the deeper place up to now available in the mine. In the middle of next year, we will plan, as Luca already anticipated, a monitoring station for magnetometer for magnetic noise, sorry, composed by 3 sensors oriented along the 3 spatial directions, and also the installation of a microphone at the remaining deep caves. So these are a very brief conclusion. The installation of the environmental monitoring infrastructure is ongoing. We had a lot of delay this year due to the COVID, as many other activities, of course. And up to now, only weather station and underground magnetometer are regularly stored. We plan to do this also for other probes starting by January of next year. And the electromagnetic noise is very low, as expected, if compared with other instrumented sites like Virgo or other places in which a large amount of electronic devices are working. And that's all. Thanks for your attention.
Thanks to you, Rosario. You are more than 1 minute in advance. So we have time for questions. I see there is a question on the chat. How much is the conductivity of the rock soil? Ah, no, it's not maybe for you.
Yes, I'm sorry, but I'm not able to answer to this question.
I don't know if there are questions or comments about your presentation.
Yeah, but this is about the damping of the Schumann resonances. So the question.
So actually, I compared the spectra, in particular the Schumann resonance between surface and underground. They are very similar, and since they are very similar, I need to do a better work on the site. I plan to go on site in next time in order to be sure of the calibration of a single magnetometer. Each magnetometer has a calibrating utility inside, but I cannot operating by remote. So I need to go on site, perform a accurate calibration by injecting the signal inside in order to be sure about the exact calibration, few percent, I mean, between the two instruments. And then after this work, I will be able to compare the amplitude of the Schumann resonance between, and the difference between surface and underground. I do not expect large difference in any case.
Thank you. Are there any other questions? Sorry, I was without glasses, so I didn't see Schumann resonances after the. Okay, if not, thanks again, Rosario. Now the next speaker is Enrico. Enrico will give another talk about the study of seismic noise at Sostenatos. Enrico, are you there online?
Yes, can you hear me?
Yes, I can at least.
So
you can try to share your screen.
The screen. Window.
Okay, you have 15 minutes.
The presentation.
Now. Yeah, it's visible. You can start.
So I will talk about the seismic noise again, but looking at the non-stationarity, and in particular in connection with the search for intermediate mass black hole. I listed all the people that I have in mind, and so I excuse for the people that eventually I forget. So the motivation of this analysis is this. When we go toward the 2 Hertz, we open the window for the observation of the intermediate mass black hole, the coalescing binaries, of course. So their signal lasts in the detector about 1 minute, we will see better. And the frequency of the signal of the in spiral phase lies within the 10 Hertz band. So considering the Newtonian noise, which is the main noise that we have to face at so low frequency, one can ask himself what is the probability for a signal lasting 1 minute to have the noise in the bandwidth higher than the target noise. So what I used for this measurement, for this analysis, is the seismometer placed in minus 84 meter station, which is the one that you already have heard, that is the one with the best sensitivity that we have placed in the mine. So, first of all, let me very well clarify what I used to calculate the coupling of the Newtonian noise to ET. So the equation is the one that you see here. And for further clarification, you can look at the paper of Jan Harms and co-workers. the one point that I have listed here that it is yet to clarify is how the Newtonian noise is correlated in the 3 interferometers. Because we have, if you take a glance to the interferometer here, to one end, one corner, we see that input masses of one interferometer lies not very far away from the end masses of the other interferometers. So the signal will probably be correlated. And then I used this equation, which is again coming from Jan Armsen, which is, I think, the best assumption until now, but probably asks for a deeper understanding. Then we have to define a time window for this analysis. And here there is some arbitrarity. So first of all, of course, we focus on the sources that have a spiral phase within 2 to 10 Hertz. Clearly, in this case, the motivation is that in this case, the signal is clearly distinguished by the noise because of its frequency amplitude behavior. I mean, it is just not a glitch. It's having a spiral phase. And then by using the very well-known equations, we take as the final frequency, of course, 4 times the frequency of the last stable orbit. Under this assumption, the time before coalescence, once that the signal enters in the bandwidth, spans from several tenths of seconds to minutes, depending on the parameters of the binary decoalescence. And so we chosen a mean value of 1 minute for this starting of the analysis. Then, before the analysis of the glitches, let me take a glance again to the median. The interferometer was installed the seismometer was installed in June, July. So we take the data from the 1st to 26th of August. Here, when I refer to nights, means from 9 p.m. to 3 p.m. local time. And when I say about holidays, I take from 8th of August to 23rd of August. This is partially the same things that Sacrotti has shown with respect to the COVID period, to the lockdown period of March. So we see that under this condition, I mean, at 84 meters, we see that in the red curve, which is the median on the whole period, the noise, the Newtonian noise, is, I mean, under, the median is under the target sensitivity for the frequency band from almost 3 Hertz to 10 Hertz, and is a bit higher than the target around 2 Hertz. This situation gets slightly better in the holidays time, and it is far better, really better than what expected, I mean, during nights. Here I make a comparison with Tertier. So this is the median of SO1 in August. So this is the median of Tertier during the same time. So in Sosenatos, these results are encouraging, but as I said before, we have to say we have to look at what is the glitches behavior. So we defined a noise estimation, which is a noise to target ratio, which is here in this equation. You see this is the power spectral density of the noise, Newtonian noise, And these are the denominator, that is the power spectral density of the AT sensitivity, of the target sensitivity. So if this number is equal to 1, this means that the Newtonian noise is equal to the target sensitivity. If it is higher than 1, it is a worse situation, because it means that the Newtonian noise is higher than the target sensitivity. We must remind that in the region of 2 to 7 Hertz, this is exactly what we expect, because it is expected, the Newtonian noise is expected to limit the sensitivity. So this measurement is exactly a measurement of if we are fulfilling our requirements or not. So this is the time behavior of these glitches around 1 day. So here you see that during 1 day, if you start at 0 minutes, means at midnight UTC, to 2 a.m. local time, there are essentially no glitches, let me say, overcoming 1. So this means that here, if gravitational waves arrives, the noise is not degraded by the Newtonian noise. Then if you enter inside the working day, I mean during the day, then you have several glitches. And during night and late afternoon and again night, you don't have anymore a lot of glitches. This is the same picture, but all over the period of days that we have looked at. So sometimes, for example, here, you have a higher number of glitches, always during, midday, because here, please, we have to remember that the mine is still accessed, as Sakuroti has already said. So indeed, if you look at the second part of this plot, which is during holidays, you see that there are clearly less glitches than during working days. So finally, our distribution is this. If you take the whole period, the probability to be, again, if in 1 minute, in a certain minute, if a gravitational wave arrives, the probability to have a noise lower than target sensitivity is 60%. If you admit not large, small deviance from unity, you have 80%. If you go during nights, you go to 80% of probability to be less than target sensitivity, or 95% to be below 1.5 of this noise to target ratio. And finally, you will see comparing
4 minutes.
Sorry, 5 minutes.
Four. Sorry, I was following your presentation and forgot.
Okay. Oh, sorry, I will go very fast. So again, here you see that during holidays period, this rises to 76% and 86%. I make a comparison, a fast comparison with Tertier, with the same analysis in the same time. And here you see that the probability to be less than 1 is negligible. If you reduce by a factor of 3, thanks to Newtonian noise cancellation, this would bring the probability to be less than 1 to 64%. And with a factor of 5, would bring the probability to be 92%. Remember that this is seismometer already placed at 205 meters. Then I take a glance also to L-shaped, supposing 15 kilometers L-shaped, so that we have the same tunnel length. So in case of Senatos, the noise becomes almost compatible with expectation, because the probability becomes 86% and 1.5 94%. But the situation relaxes also for Tertiaire, because you see that with a noise cancellation of about a factor of 3, what is outside, I mean, the requirement is a small fraction of the time. This is almost all. So the conclusion are that, again, you have already said, no degradation if in particular we have the 15-kilometer L-shaped. Of course, in case of source and actors, Newtonian noise cancellation will improve the AT sensitivity with respect to target. This, what you say, is an August day, so this, I think, should be called anthropic noise. That is something that we don't have completely under control, I mean, in the mine. So the next step are essentially 3. We have to better estimate the Newtonian noise coherence in the triangular multi-interferometer shape. We should weight the probability with expected high intermediate mass black hole populations. And another point that we are looking at together with Saccorotti is to identify very local noise sources, to better understand what is the natural noise sources and what we have to do in designing AT infrastructures to not have self-noise generating infrastructure. That's all.
Thanks, Enrico. You are 1 minute in advance. So we have time for questions or comments. Okay, actually, I have a questions. Your calculation is referring to a model. The calculation that you did about the Newtonian cancellation. Enrico, can you hear me?
No, can you hear me?
Yes, I can.
Okay.
The calculation that you did about the Newtonian noise cancellation was referring to a specific model, the one published by Jan, right?
No, here I am not saying let's say anything about the Newtonian noise cancellation. I want just to say that relaxing Newtonian noise cancellation requirements can be of help, of course. I am not stating that making a Newtonian noise cancellation that is effectively as a reduce for 5 times the noise of 3 times the noise easy or difficult. This I don't enter in this detail. I think that it is interesting for all of us to see what is the status and maybe to see that this can be relaxed by, or will be relaxed if we use an L shape.
Okay, thanks. There is a question from Michele.
Yes, thanks, Enrico. Let me understand better. There is a point that I missed. The difference between the triangular shape and L-shaped detector in the performance. What is the source? Is due to the correlation between different detectors? It's not clear to me why the L-shape and triangular have a different performance.
L-shape, we know how to calculate it. L is 15 kilometers instead of 10. And I mean, the calculations are in some sense more, let me say, solid, sorry for this term, because these calculations are longer and so on. In case of triangular shape, I used what it is known up to now, which is the equation that I showed in the first pages. In this equation, as you see, there is this equation is a sort of intermediate step, because we don't consider the noise completely related, because otherwise you would see there the effect of the angle in the sensitivity. So we don't consider it as a single interferometer, but we consider it as a not completely decoupled interferometer. So it is an approximation that it is used until now. So with respect to this approximation, L is easier to calculate. We know the formula for that.
You were the next one.
Yes, it was already remarked by Harold in the chat window. As soon as you start comparing noise spectra at different sites, then you need to have a detailed model to convert what you observe there and the geology there to an estimate of Newtonian noise. So I don't think you can do anything generic about this.
Sorry, I didn't understand the question.
The question was that if you have different sites, what you are doing is you're comparing different sites and you're making statements based on a generic Newtonian noise model about what could happen on the detection of IMBHs. So what I'm saying, if you do that, then you have to be careful about how you calculate your Newtonian noise.
Yeah.
So there is a model aspect going into that, which determines how what is the influence of geology, how do you weigh surface waves and body waves and things like that. So I think to make that generic statement that you do, I would be a bit careful.
Yes. So this is not exactly a question, but maybe I can answer. The equation that I use to calculate the Newtonian noise is exactly the equation that you used to make the SP proposal. I am not using, so if you use this calculation and you put inside the hypothesis on seismic noise that we all placed toward the SP proposal, you find exactly the curve that it is in the SP proposal. So I use it exactly that.
Yeah, no, that's fine that you do that, but it doesn't change my remark.
I checked it 1 million times to have exactly the same result.
No, Enrico, I see that. I'm not arguing with that, but it still doesn't change my point of view.
So maybe I can say 2 words, because that's so first of all, Enrico didn't include anything from the surface. So the geology has a very small impact on these results. This is only body wave Newtonian noise. So that should be said. Surface wave Newtonian noise strongly depends on surface, but this is not even included in this estimate. The other thing is, of course, that there are, of course, things that are important that Enrico cannot model correctly now, like, for example, anisotropies in the seismic field. All of that matters for sure a lot, but this is information that we simply don't have. But just to say, geology has a very, very little impact on the results that he showed, because it's just body wave Newtonian noise. Another thing that I wanted to say, however, was about the triangle versus L. So I think that the fact that the noise can be correlated at low frequencies has, of course, some significance. But I think this is more to understand what we can do with the null stream to reduce transients, the transient instrument background. Because in principle, the null stream allows us to reject transients as distinct from signals. But if you have correlations at low frequencies, then this will not necessarily work anymore. So that is the part that you can think. And this is something that you didn't take into account, that in principle, a lot of that background, that is the transients that are still at low frequencies and that you analyze, they could potentially be rejected. But this definitely depends on the correlations that you have at low frequencies between detectors, because that determines the efficiency of the null string.
Yes, two things on this. Of course, on the last point, I agree. Let me first ask you the first question. I didn't take into account in this calculation the surface, what in our understanding are called the surface waves, which is not the same things that the geologists call surface waves. So for us, surface waves are waves which are very high at the surface and then are attenuated when you arrive at minus 200 meters. In this case, I didn't take into account this because the effect of these waves, as I shown already, twice yesterday, is to couple directly through Newtonian noise from the movement at the surface via Newtonian force. This is not a problem for Sosenatos because in Sosenatos already the noise is very low at the surface. This is a problem for Tertiaire. In this sense, I didn't make this calculation because I think that this is a problem that could get worse, would make this calculation, this comparison worse. But due to the fact that I am not sure of the effect, I didn't place it. And I said in this presentation that I only take into account of the body weight. For the second part, which is the coherence among interferometers, I think that especially in the triangular shape, I agree on the fact that it is something that we all must to understand better, for sure. As I said in the first slide.
No,
I understand that you can reject a signal which is which does not fulfill the null specification. I mean the null equation. But this does not mean that you don't have the noise. If you are blind by noise, you can say I am blind, but this does not mean that you can open the eyes.
Yeah, I can say many things, but I think maybe because of time we should carry on.
Yeah, thanks, Enrico. I'm sorry, but I have to stop the very interesting discussion. Jan, I see that you still have your hand up. I don't know if you, okay, just to know. Thanks, Enrico, again. This was the last talk about the studies ongoing at Sosenatos. The last talk of this session will be done by John Osborne, an engineer from CERN. And this talk will be about the civil engineer studies done at CERN. This is one part of the interaction that we are having with the CERN staff and try to benefit from their experience in the underground and construction. John, are you there?
Yes, I am. Good morning, everybody.
Good morning, John. Enrico, you have to stop your sharing. Thanks. John, could you try to share your screen?
I'll try my best. Right. How do I move these cameras there, isn't it? Okay, is that okay? Can you see that slide?
Yeah, I can.
Okay, so good morning, everybody, and thanks for this opportunity to talk here today. So it's been very interesting listening to the talks this morning. I think there's lots of areas of synergy in what we do at CERN, what you're doing for the Einstein telescope. So as was mentioned, I'm just going to give a brief report on how we manage sighting studies at CERN in the past and in the future for future accelerator studies we're working on. Just a very quick introduction for CERN Geology. We're in a, mostly in a soft rock called molasses. It's sedimentary rocks. We try and house our machines in that rock as much as possible. But we also have some limestone in the area, which we try and avoid if possible. We have about 70 kilometers of existing tunnels, more than 80 caverns. What you can see at the top is the LHC, but we also have a lot of accelerators leading up to the LHC. So, of course, in the past, for the LEP machine, there was lots of discussions like you're having about the sighting of the 27-kilometer LEP machine, shifting it around the area to get the best possible optimized position for cost and schedule, which I'll come into on the FCC and the Future Circular Collider, which is a very similar exercise to what was done for LEP. So our geology in this region, we have glacial deposits on the surface, which we have to go through with the shafts to get down the tunnel. And then we have this molasses rock, which is a good rock for tunneling. It's fairly impermeable, dry rock. However, it's quite soft, so it needs quite a lot of support. We have to have a strong concrete lining to support the ground. And then we have some limestone rock that we try and avoid. We went through it for LEP in one sector, where we had some water ingress from these natural occurring cavities, water and silt, coming into the tunnel. So we try and avoid the limestone if possible. So a little bit about the past. This is the LEP machine in grey, the 27 kilometers. As I said, it was shifted around quite a lot to get the best possible location. And then once it was fixed, we could have a choice for the LHC. These are the big work sites we did in the 90s, early 2000s. Work sites in France for CMS detector, and similarly on the Swiss side for Atlas in red, the new underground construction works. To convert the LEP into LHC cost about 500 million Swiss francs. We typically find for our type of contracts, we need about 10 to 12% for the design, for the consultants to do all the tender design, construction design, project management, and the rest goes on the contractors for the construction works. So that's a little bit on the past. On the present, we're now building high luminosity LHC. What you can see in red, the 0.5 in France for near to the CMS site, and then in Switzerland 0.1 close to the Atlas site. So this is, I think, quite relevant for you. I don't know what your contract strategy is for all the procurement for these works for civil engineering, but we used for LHC and for high luminosity, we used the same procurement strategy. We used FIDIC type contracts, international form of contract, where it's a remeasurement based type of contract. So we place two major contracts, one with the consultants for the design of all the works, from the tender design, construction design, all the site supervision, project management, right to the end of the works, and then a separate contract for the contractors to do the execution. So the works were not designed by the contractors, they were designed by these consultants under a separate package. And then to speed things up a bit, we placed early contracts with architects to do the building permit submission with the local authorities. And we decided for the high luminosity to have two separate contracts, one for the French side, one for the Swiss side, not just because we're in different countries, but also for strategic reasons, in case we had some issues with the consultants or the contractors underperforming or having financial difficulties. And we had the possibility to swap companies around, which is in fact proved to be very good, a good idea and a good incentive for the companies working on it. So we had many discussions about where to build the shaft. We have, unlike your sites, I think we have lots of restrictions on surface. So the location of the shaft in these buildings is very delicate. So it has an impact on the whole orientation of the underground works, what happens up on the surface, of course. And then how we link into LHC. We had a live machine. LHC was working during some of the civil engineering works. So we had lots of discussions about vibration and how we could do the works without impacting on the LHC. So lots of things to consider before we could embark on these civil engineering works. Similarly at 0.5, it's a similar layout in blue this time. This is the new shaft, new cavern for high luminosity, a gallery running parallel to LHC, about 300 meters long, and then 4 connecting tunnels over the top of the LHC. And then we're drilling cores down to LHC in a different shutdown of the machine. These are the 2 construction contracts that we placed, roughly about 70 million francs per site for the French and for the Swiss side. And the works have gone very well, in fact. They're a little bit behind program. Obviously, we had the COVID difficulties, but we found the form of contracts, these FIDIC contracts, suit physics projects very well, because it gives you some flexibility to modify your designs during construction using variation orders. Of course, you don't want to do that. You want to try and have everything fixed before you start construction, but inevitably with these type of contracts, it takes such a long time that things do change. So we tend not to use design and build type contracts a lot for this type of work, because we're a little bit uncertain when we place the contracts to exactly what the requirements are. Just a few pictures for high luminosity for the construction. This is the shaft and the excavation of the tunnels and caverns. So as I said, it's quite a soft rock, so we can use a hydraulic hammer to excavate the rock in most cases, or a road header type machine. We don't use drill and blast. It's not really worth it for these small works. The excavation is virtually complete. What's quite interesting, I think, for your project is we're very sensitive to water ingress coming into the caverns. So we have this waterproof membrane in our tunnels, everywhere in our tunnels, in fact. So we have a primary lining in the top left is a sprayed concrete lining initially. At the end of this tunnel, you can see the actual rock on the top left face there being excavated. So we have this primary lining, shotcrete, then we have the yellow waterproof membrane, and then we have the in situ concrete with reinforcing steel to support the ground. So any water that manages to get through this primary shotcrete lining is captured by the waterproof membrane, drained to a central sump, and then pumped out of the tunnels up the shafts ultimately. So I don't know what your design is for your secondary lining, or if you just have a primary lining, I'm not sure. But we always have a secondary lining, and another reason for that is not just the support of the rock, but we also like to have these precast, these inserts in the secondary lining, which are more difficult to do in a primary shotcrete. For example, these half-fin channels and steel plates to allow services and equipment to be installed more simply and quicker at a later stage to avoid drilling into the concrete. And we also have this dust protection. We're very sensitive to dust, so we have this dust protection paint on all our linings, whereas with a shotcrete you tend to get a more dusty environment. I'm not sure what your requirements are with regard to dust. So that's what it looks like on the surface now at 0.1. We also have a lot of surface buildings that we need. These are the ventilation towers on the Meyran site, close to the main CERN campus, and several other buildings. But it's quite important the amount of space you need, of course, for the contractors and the design companies. These barracks here are just for temporary installations for the companies, and these buildings on the left-hand side as well. This big hangar is just a temporary building over the top of the shaft, just to allow the excavation of the works and the construction of the underground areas. And we also have a problem with the handling of the spoil. We have some contamination in this region with hydrocarbons. So you have to, first of all, test the rock and then separate it out and send it off to different deposits depending on the degree of contamination. I guess you'll have a similar thing with your drill and blast. You'll have some chemical contamination in the rock, which you'll have to filter out and send it to different deposits. So it's an important aspect to think about in advance is the spoil. So the future, that's the past, present, and now in the future. So we're now working on future projects like the Future Circular Cloud, the FCC. Of course, these projects are very long in the pipeline, from feasibility studies through to design, construction, up to ultimately physics. So it seems a long way off having to start thinking about a future circular collider when we're just finishing high luminosity civil engineering. But in fact, to match the physics program, we're already becoming on the critical path now if we're going to build this machine to get going with the real feasibility studies, the design and the construction to be ready for after high luminosity LHC. So we've been working on this for a few years on the FCC. This is the Large Hadron Collider, 27 kilometers. And we'll be looking at the siting of approximately 100 kilometer machine in the region, and it's very much driven, well, of course, primarily by physics, but also it's very closely driven by civil engineering. We were asked to decide what we can fit in the region within reason for a reasonable cost in good rock. Also, future projects like CLIP we're working on, the linear colliders, where we have more freedom to move it around. We're not constrained by the LHC. But again, it's very much driven by civil engineering. And then we also have many other studies under a different umbrella called Physics Beyond Colliders, where we're citing these machines with a big importance on civil engineering. So the European Strategy Update in 2020 gave us the green light to go to the next stage of feasibility for the FCC, which we're doing now. We've looked at many different options for the FCC over the years. For example, in this bottom left-hand corner, you can see originally we thought about having the FCC completely to the northwest of CERN, going into France in the limestone rock. But for various civil engineering risks and strategic point of view, we didn't do that. We're now focusing on what we call the CERN option, the lakeside option, with a 100-kilometer tunnel going underneath Lake Geneva around the back of what's called the Slave Mountain. And a big consideration, as I mentioned, is the spoil, what we're going to do with this excavated material. So what I think is relevant for you is how we cited the FCC in the geology. How we did it was we developed a software tool that I think I mentioned before in a previous telescope conference. So this tool was very, very useful for us to look at many different options of the machine very quickly and see what geology we're passing through. So we can move the machine, the FCC, within a certain study boundary. We can play with the depth, the inclination of the tunnel, and then the software gives the depth, the shafts, and the different geology we're going through for the main tunnel. This is a long profile around the 100-kilometer ring. For that, you need good input, of course. So we got as much data as we could that existed in the region for the different types of rock. And this is what we have in our conceptual design report: a 97-kilometer tunnel, 90% in the good molasses, a little bit in the limestone, and a little bit in the glacial deposits underneath Lake Geneva. So that's what we're working on at the moment. That was our first feasibility study. That's a schematic of the machine, what it looks like. This is the 100 kilometers, the blue tunnel with shafts every 10 kilometers. So you can see there's lots of different civil engineering structures required. And this is a big integration effort, working with all the different partners around the world for providing different components to get one model for all the civil engineering. And I think this is very relevant to you, how we did the cost and schedule studies for FCC. So we asked two companies to do a cost and schedule. I'm just talking about civil engineering here. And it took us about 1.5 to 2 years to do this for cost and schedule. For our first estimate, we were very, very cautious not to announce any numbers until we had a robust design. It's very easy to give a number very early on in these projects without having a design of it, much of an idea what you're going to build. We really try not to do that. So we spent a lot of time looking at gathering the requirements, integration studies, and we worked with these two companies doing cost and schedule for the civil engineering. For that, of course, you have to have your tunnel different lining concepts for the different types of rock. So we made quite a few assumptions, assuming what type of tunnel excavation and lining will be required. And that's the construction strategy that we came up with now. So we're looking at least working from every shaft, so 12 different work packages, constructing the civil engineering in parallel with 12 tunnel boring machines or drill and blast in certain locations. The type of TBMs, the tunnel boring machines, comes into it as well, because that has a big impact on the cost. What sort of lining you're going to use is also impacted on the tunnel boring machine. And that's our first schedule for FCC. We're looking at about 7 years for the civil engineering. That's for an empty tunnel without all the equipment, the ventilation services, etc. So this is our planning now. We got the green light from the European Strategy in 2020 to continue with the feasibility studies. So now we have a certain amount of money. We have about 15 million Swiss francs for high-risk site investigation. So that's not enough to do all the site investigation. We estimate typically for these sort of projects, we need about 2 to 3% of the civil engineering costs for site investigation works, which in this case amounts to up to nearly 100 million Swiss francs. So we haven't got that. So we're only doing what's called the high-risk site investigation in the most critical areas for the next few years. And then we'll update the CDR, the Conceptual Design Report, which will feed into the next European Strategy update in 26-27. So that's our focus for the next few years, this high-risk site investigation. We know more or less some of the areas underneath the lake, for example, is going to be critical. This area going towards the Alps. This is what we're working on now, identifying the critical areas and coming up with a plan for site investigation within the funding we have. I'm nearly finished, a couple of slides.
Yeah, your time is over.
Okay, two more slides, just finished. I think it's very relevant for you. Somebody mentioned it in one of the earlier talks, is all the software tools that you're going to use for geological data and for the machine modeling, etc., and the surface. So we're using ArcGIS as our central repository. And a little bit on, we're not as concerned as you are, but there is some faults, geological faults in the area. So we're thinking of setting up a seismic network to monitor these faults for the civil engineering works. So, and for the machine itself. So in conclusion, I think we have a lot of experience in CERN on siting these types of physics projects from a civil engineering perspective. I also work on CLIC, ILC, and Beyond Collider. So we have a lot of experience in costing, for example, and planning for these sort of things. And now our next step is to work on the high-risk site investigation for FCC, which I think you've got a similar campaign being planned for your project. So that's it. Thank you.
Thanks to you, John, for your nice talk.
Yeah,
is there a question or comments?
I have a question. Can you?
Yeah, go on.
Yeah, hear me. Hi, Frederick Nian. I was just wondering if you consider the early contractor involvement stage rather than to have the design separated from the contractor phase.
Well, traditionally at CERN, we don't really do that because in the past, it's very difficult to define what you want for these type of projects early on. So we tend to spend a lot of time with consultants iterating the designs before we place big contracts with the construction companies. But I think for FCC, it's such a huge project. We're going to look at all sorts of strategies for the procurement. You're right. Maybe early contractor involvement could be adopted for the FCC. You're right, but we haven't done it in the past.
All right. Thank you.
It also depends on your procurement rules. I mean, CERN's been around for 50 years, and we have a very, very well-established procurement procedures, whereas you have an opportunity, I think, to start from something new.
Right. Thanks.
Are there any other questions?
Even though you spend about 2 to 3% of your budget on these preliminary studies, there is still a remaining risk. Is there any way to cover that risk? How do you address that?
Yeah, of course. The risk is a big part of the. This is why we're doing the high-risk site investigation studies now, as soon as possible. I mean, a lot of people are arguing we don't need to spend this amount of money on this site investigation because we know the CERN region, we know the geology. But in fact, it's not the case. We think it's very important to spend a considerable amount of money on this site investigation, in particular in the high-risk areas where we think it could have an impact on the vertical and horizontal alignment of the machine. So there's going to be a lot of iterations, I think, on the civil engineering layout, and there's a lot of risk. For example, underneath the lake, we're putting it through the moraines at the moment, to glacial deposits, because that reduces the cost of the whole complex. It makes it less steep. All the shafts become less steep, so you're saving money, but the risk is increasing. So that's what we're going to look at in the next few years. Is this risk worth taking to minimize the cost for the shafts? Are we taking a bigger risk by going through these glacial deposits? So you're right, it's a big part of the next few years, yeah.
John, I have a question about which is the expectation about the cost of the contamination of the rocks that you can find? I mean, in terms of the analysis that you have to do, in terms of the operation that you have to implement to separate the rocks.
It's very difficult to predict for FCC. Even when we did the high luminosity works, we did a lot of site investigation for the LEP, for LHC, and then for high luminosity, we thought we understood the geology, and we still had surprises for high luminosity. The site in France, we came across a lot of hydrocarbons that we didn't really expect. So imagine for a 100-kilometer tunnel in geology we don't know, it's very difficult to forecast what the contamination will be. So to be honest, for I think what we're going to have to do is just look at the experience we have from high luminosity and just take an average for the cost risk at the moment. We're never going to test every kilometer around the 100 kilometers in great detail. So we're going to have to just come up with some reasonable risk assessment for what we expect to discover. But it's tricky, and the legislation is changing. In France and Switzerland, it's different rules. In Switzerland, are quite strict, more strict than in France. So it's a very complex analysis what it's going to cost. Yeah.
Can I ask a question to John?
Go on, Florian.
John, I have a question. How many of your shafts you can race drill, and how many you have to build drill and blast or conventional?
Yeah. Well, the problem is with this, not a problem. The issue with the CERN shafts is they're generally quite big. The minimum size shaft we have is about 10 to 12 meters internal diameter, because we need all the services going down, the ventilation, electricity, and lift. So we've heard, I think on the Turin tunnel, they're doing raised drilling for very deep shafts, 500 meters deep, I think. But they've told us the biggest they can do is probably 4 or 5, maybe maximum 6 meters, I think. So it's not really big enough for CERN. But of course, we're thinking about it. Maybe we could do multiple shafts rather than one big one if it's cheaper.
Okay, thanks.
Sorry, how many TBM are you going to use at the same time? Or at least which is your plan?
Between 10 and 12, we think.
10 and 12.
Which is not, some people say that's ridiculous, but it's not. On similar projects like the Grand Paris, there's a similar number being deployed now. So it's not unheard of.
Thank you, John. If there are no other questions or comments, your talk is the last one for the session today. Yeah, there was someone else? No. So the session is over. See you tomorrow. Thank you again, John, for your contribution.
Thanks, everybody. Thank you.
Thank you.
Bye-bye. See you tomorrow.
Bye-bye.
And we restart at 3 the session with science, if I'm not wrong. See you this afternoon.
Bye-bye.
Bye-bye.
Bye.
Bye.
Bye.